Hello everyone, I am Dr. Subhasish Saha, Assistant Professor in Physics, Department of Humanities and Science, MLR Institute of Technology, Hyderabad. In last video, I discussed what is quantum physics, what is the origin of the quantum physics, and how the evolution happened in quantum physics. In today's video, I will discuss about the black body. What is black body? What is black body radiation? How the black body radiation spectrum how the black body radiation spectrum evolves as a function of wavelength for different temperatures, and how to describe the black body radiation spectrum by Planck's law and some other scientists. Those topics today I will discuss. So the today's topics overview is black body radiations, Wien's distribution law, Rayleigh-Jeans law, Planck's law of radiation. It is a quality discussion, and Stephen-Boltzmann law. So first of all, what is black body? Black body, ideally a black body is that absorb the radiation of all wavelengths incident on it. This means when the radiation incident, that will absorb the entirely all the radiation it will absorb. This means absorption coefficient is 1, means it is 100% absorptivity. But in reality, no perfect black body exists till date. Example, some of the example is sun, heated iron, practical black body, like Fairy's black body. So practical black body means it was constructed in lab. First, it was constructed in lab by Fairy. So it is the schematic diagrams. So what is how actually it is constructed? So let's suppose in the lab, it has constructed like a spherical shell, a spherical hollow shell with a small hole. Okay, this is a spherical shell. Okay, and in this spherical shell, there is a small hole is there, and the outer wall is silver polished surface. So to prevent the absorption of outward radiations, for that silver polished surface is coated, silverly polished the outer surface. And what will happen, let's say the radiation comes and enter through this hole, okay, and it will incident on the inner wall where one canonical projection is there. So due to the presence of canonical projection, the multiple reflections happen inside the cavity region. So, and these processes continue until the entire radiation is absorbed, and the inner surface is coated with lamp blacks. This means it will absorb the 97% of the incident radiation. Okay, so the loss will be less due to the presence due to the inner surface is coated with lamp black. So in this way, what will happen, since the entire radiation is absorbed, the wall of the black bodies are heated to a temperature, and the radiation come out through this opening channel. So in this way, the cavity walls are constantly emitting and absorbing the radiations, and these radiations are giving us the black body radiation spectrum. Now, so in next slide, I'll discuss what is the schematic diagram of black body radiation spectrum. This is a schematic diagram of black body radiation spectrum. So into this figure, actually it is described how the intensity of the radiation spectrum varies as a function of wavelength for different temperatures. So in these diagrams, if we notice, when the wavelength is very low, the intensity of the radiation started from very low value. As the wavelength is increased, the intensity will gradually increase and reach up to a certain maximum values, okay, corresponding to some lambda value, that is denoted by lambda m. After that, it again, the radiation spectrum will decrease with the further increase of wavelength. Okay, so this means at a given temperature, the intensity of the radiation increase with the increase of wavelength. At a particular wavelength lambda L, its value reach to a maximum value. Okay, with further increase of wavelength, the intensity of radiation decrease. Next point is that if you notice, if the temperature is gradually decreased, the intensity of the spectrum is also decreases. This is quite common and natural. If the temperature gradually decreases, the intensity of the spectrum will also decrease. So this means there is a decrease in energy emission with decrease in temperature corresponding to all wavelengths. And another important point, we notice that if the temperature decrease, the peak of this value, the peak value of this intensity radiation spectrum will shift it towards the higher wavelength region if we decrease the temperature, that is denoted by this dotted line. Okay, this means with the decrease in temperature, lambda m is, these are the lambda values where actually the peak values are, we observe this lambda L increases. Okay, so this point on the dotted line represent lambda at various temperature. So these black body spectrums actually successfully explained by the Planck's in 1990. But before going to that discussions, some other scientists in the late 18th century and the early of the 19th century, some other scientists give some explanation to describe this black body radiation spectrum. Let's see what are those. First is, in 1896, Wiens proposed some law that is called Wiens law, actually where he mentioned that the energy density distribution in the wavelength range lambda and lambda plus d lambda at a temperature is given in this form, okay, where E lambda d lambda equals to 8 pi hc by lambda to the power 5 into e to the power minus hc by lambda kt d lambda, where h is the Planck constant, c is the velocity of light, k is the Boltzmann constant. So this law is valid only for the shorter wavelength region and low temperature region. This means when the wavelength is very low and temperature is also very low, this means lambda t is much less than 1 and e to the power hc by lambda kt then much greater than 1. In that case, this law is valid only. In 19th century, exactly in the 1900 time, the Rayleigh-Jeans also proposed a law, that is that Rayleigh-Jeans proposed that energy distribution of radiation of a spectrum is given E lambda d lambda equals to 8 pi kt by lambda to the power 4 d lambda. This Rayleigh-Jeans law is valid only for the longer wavelength and high temperature region. This means when the lambda t is much greater than 1, then e to the power hc by lambda k is much less than 1. That time this law is valid only. So this means these laws has some limitations. Wiens law is valid only for the shorter wavelength region and Rayleigh-Jeans law is valid for longer wavelength region. So to overcome these things, on the exactly same year in 1900 times, Planck proposed his laws of radiations to describe the black body radiation spectrum, and this law is successfully explain the black body radiation spectrum over the entire space in low wavelength region as well as in longer wavelength region. For these things, Planck gives some assumption. What are those assumptions? First of all, black body radiator can be treated as a simple harmonic oscillators which are capable of vibrating with all possible frequencies. And the second assumption is these oscillators radiate energy in a discrete manner and not in a continuous manner. So this second point is very crucial. Actually, this is the fundamental difference from the classical laws of physics, where classically when tried to explain the black body radiation spectrum, it was considered that the energy spectrum is a continuous manner, but first proposed Planck's that not, it is a discrete manner, it is not a continuous manner of the energy spectrum. So due to this fundamental difference, he is able to successfully explain the black body radiation spectrum. The third point is then the oscillator exchange their energy in the form of either absorption or emission, okay, in terms of emission of energy in terms of quanta of energy, okay, that is h nu. This means E equals to h nu, nh nu, where n equals to 0, 1, 2, 3 and so on. This means the exchange of energy will not take place continuously but are limited to a discrete set of values 0, h nu, 2h nu, 3h nu, so on. Means it is a integer multiple of h nu, where h nu is the energy of a photon, and this introduced the concept of energy quantization. So based on that, we can say that thus the oscillator can emit or absorb energy in a packet of h nu. On the basis of the above assumption, Planck's reduced the formula is E lambda d lambda equals to 8 pi hc by lambda to the power 5 e to the power hc by lambda kt minus 1 d lambda. So this is a general expression. From this expression, entire black body radiation spectrum can be explained for low wavelength region as well as in high wavelength region, and this law can be reduced when the, let's see, lambda t is much less than 1. That time what will happen? E to the power hc by lambda kt is much greater than 1. That time this law is replaced by Wien's law for low wavelength region. For high wavelength regions as well as when lambda t is much greater than 1, that time e to the power hc by lambda kt is much less than 1. That time this term we can binomially expand, and that law, this expression will replaced by Rayleigh-Jean's law. So that's why this expression is a general expression. So for the course curriculum for applied physics for BTech students, this is only the quality discussion is there. There is no derivation is there. Next, come to the some other points given by Wien's, that is called Wien's displacement law. From this figure we notice that if the temperature goes down, the peak value is shifted towards a high wavelength region. So from this phenomena, Wien's displacement law states that the black body radiations curve for different temperatures will peak at different wavelengths that are inversely proportional to temperature. This means formally the product of wavelength corresponding to minimum energy and the absolute temperatures is constant, means the product of lambda mt is constant. Okay, this is called Wien's displacement law. Now come to the Stefan-Boltzmann law. So it is also used to explain the black body radiation spectrum. So what is the statement? The statement is that total energy emitted or radiated per unit surface area of a black body across all wavelengths per unit time is directly proportional to the fourth power of the black body's thermodynamic temperature. This means the energy emitted per unit time, this means that is here P, power per unit surface area is proportional to the temperature, fourth order of the temperature. P by A proportional to T to the power 4, and that proportionality constant is Stefan constant. The value is that this one 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So these are the some laws or some explanation proposed by the scientist to explain the black body radiation spectrum. So in next video I will come up what is matter wave, what is the properties of matter waves, de Broglie hypothesis, and the experimental evidence of the matter waves using Davis and German experiment.